All right, we are live. Uh, Thanks everybody for coming for this session. If you're wondering where you are at the Decentralized Knowledge Graph track. So if you want to follow along the agenda, please go to that link or the QR code is also here. So we have exciting set of talks lined up from 9 until about 2:30, and then we'll have an informal discussion. So I first of all want to thank the KGC organizers because they took up uh, on this offer and gave us a chance to have this workshop. And so this is the first time we are doing this particular track, and I hope the sessions will be informative and we get to do this again in the future. So a huge thanks to Francois and Thomas Deely. And I also want to give a special shout out to the co-organizers. We have Kaiwen, Deborah, Elisa, and Branimir, who helped with the content of the program. So if you're wondering what decentralized knowledge graphs are, here's my definition. So we know that knowledge graphs are semantic networks. Blockchains are trust networks. And so decentralized knowledge graphs are really trying to connect the semantic knowledge graphs with these trust networks to hopefully do awesome things. And this is a very nascent space. And you'll see, the topics that we have today are varied. We have things about knowledge graphs, we have ontology modeling, we have governance, we have creativity. So we have lots of different talks, and we are just beginning. This is a very new space, and we welcome your feedback on this as well. So yeah, so this workshop includes many talks that discuss all of these topics. So the session one will start from now and till go about 10:30. So without any further delay, I want to introduce our first speaker. He is John Domingue. He's a professor of computer science at the Knowledge Media Institute at the Open University's Technology Research and Innovation Center. And he will be talking about towards trust and accountability in knowledge graph-based AI for self-determination. So over to you, John.
Thank you very much, Oshani. Let me just share my screen here. Oops. Sorry, let me cancel that. Let me just share with video. Thank you very much for inviting me. I'm really honored to be here. And hopefully you can see my screen now. I will just go into presentation mode. So if there's any problems, let me know, but I'm assuming that you can see everything on my screen. You can see my first slide and you can hear my voice.
Yes.
So I'm going to talk about this topic here, towards trust and accountability, knowledge graph-based AI for self-determination. This is really, really collaborative work with all of these people, Aisling Third from the colleague at the Open University, Juan Cano and Andrea Simino from the University Polytechnic de Madrid, Ruben Verbo from Ghent, who anyone in Solid would know about, Philip and Maria Esther Vidal from Leibniz, Hanover in Germany, and Luis Daniel Ibanez from the University of Southampton. So it's really a collaborative presentation that I'm giving. So I'm going to give a general motivation for where I'm coming from. I'll give an overview of the issues as we see them. Then I'll talk about 3 principles that we've come up with, 4 mechanisms which we think are important for these. And then if there's time, I'll show a couple of examples of some work that we're doing on Sparkle query validation and accreditation before wrapping up with a conclusion slide. So the general motivation for this work is from Tim Berners-Lee, really, also Tim Berners-Lee, where in this interview in Vanity Fair, he talks about the web and he worries about the over-centralization of data on the web. So, and then he has this strong sentiment saying that people have ended up producing with no deliberate intent a large-scale phenomenon which is anti-human. other elements in which centralization of data can hurt individuals. One example, which I think is significant, is there are nearly 2 billion adults across the globe who have no bank account, which means they have no access to cheap credit or loans, and this really hinders their work. So our banking system is designed where your financial data is stored in a central financial system to suit a particular set of individuals. And then lastly, I could talk about examples all day, but the last example is something that came up about a year ago. So with the Supreme Court decision in the US to overturn Roe versus Wade, a lot of women in the US started deleting their period tracking apps. So they were worried that if there's an app that's tracking their periods, this is collecting, retaining, and data which may be used one day in a court case around abortion. So, given these worries that some individuals have, I'd like to delve in for a bit for a more particular view of how we see the world, a very simplistic view to begin with. So, in the centralized world, we can think of this as a set of users. We have users that are interacting with different web applications. And these web applications are owned by companies, often large companies, and these companies own and control and manage all of the data related to the individuals. So for each user, there's a particular profile, a data profile of that user, which reflects everything that they've done and everything that's been inferred on their interactions. So from this, we see movements like the solid movement from Inrupt, which was founded by Sir Tim Berners-Lee and others, where the users can control their data in a personal data store. So the users manage, control, and own their data, and every web application has to ask permission to access this data. So in this scenario, the good news is that the users control their data, but still the companies owning the applications are still going to take maybe private data, maybe medical data or financial data, and manipulate it. So a question we pose is, in a decentralized world, how do we know that the companies are acting in a decent way? Are they doing the right thing, or what I would like with my personal data? So if you think about a single user, we have a single user using an application. The application requests to use my personal data from my personal data store, and then it takes it and manipulates it. What can I do to make sure it behaves in the right way? So one thing is that we can have a trace. We can add transparency. So we can be transparent about what data we have and what data we're sharing. The company could be transparent about what did it do with my data, what did it infer with my data, and who did it possibly share it with. So you can imagine that at least every application company would share these execution traces of what's happening, and then maybe for some, if it's relevant, I might share some execution on my side. So how do I define, is the next question, how do I define what I think is decent? So then one needs a machine readable format for describing what are my personal terms and conditions under which a company can use my data. For example, I might say that I don't want my data to leave Europe, so only European countries can deal with my data. I allow my bank to access some financial information, maybe for a mortgage application. I allow my local doctor to access some health information, but nobody else. And then maybe these are timed over a particular time that they can access them. So I share my machine readable descriptions of my own personal policies. And then every organization that uses my data has to prove to me that they adhered to their to my own personal policies and purpose constraints. Now, with this world, there are issues around anonymity and aggregation. So if we now imagine it's not a single user, but several users, then we have to think about how do we split up the traces. So if we're going to be sharing traces with every user, we have to make sure that each trace only contains relevant information for that particular user. So you're not giving away the privacy of other users. And this is an open problem as far as we're concerned. In terms of validating what's happened, we imagine that all organizations would put an encrypted version of a trace onto a verifiable platform like a distributed ledger for everyone to check. And then they would be mapped back. So I could say this personal trace that you sent to me, or the portion of the trace, actually maps with your globally declared trace of what you happened, which is encrypted. Okay, so thinking about this world, this decentralized world, we've come up with 3 principles which we think are important, which are in the title of this talk. So the first is that we need to allow for trust in knowledge graph-based AI systems. The dictionary definition of trust is a firm belief in the reliability, truth, or ability of someone or something, in this case, an AI agent. And to support this, there are 3 elements. One is comprehensive tracking of the provenance of all the data sources and the data elements used for any output, again, without giving away privacy, but understanding when I get a response, where did this come from, what public sources of data were used, understanding how knowledge graph-based AI reasoning can be repeatable, especially if the underlying data changes at different points in time. I want to understand is the same type of reasoning happening, and then having alleviation mechanisms. So if something happens where the response is inaccurate, there's a way of alleviating that that's built into the system. The second principle is accountability. So requiring or being expected to justify actions or decisions, being responsible for those and being able to explain those. So here we stress the accuracy, reliability, and transparency of what's happening in the reasoning. And this is reflected in the new or the emerging AI Act, which is coming out of the European Union. We see that there's a big difference between the symbolic world and the sub-symbolic world. In the symbolic world, where we have knowledge graphs with symbolic reasoning, we can support consistency and compliance with policy languages such as ODRL, which I will explain more in a moment, an emerging W3C standard. And in the sub-symbolic world, this is more challengeable, but there's a movement around explainable AI, which may help there. And then finally, in terms of the principles, we think about how can knowledge graph-based AI promote self-determination of citizens globally, allow users to control their life. And this breaks down into 2 aspects, which I'll expand later. First is identity. For the most part, I would assume that most people in the audience, your digital identity either comes from your employer, the organization where you're studying, or a large company. So imagine a world where everyone can create their own digital identity without reference to any of those. And then how we can move from centralized data to allowing users to have sovereignty over their data through mechanisms like solid pods. Okay, so there are 4 mechanisms which we think can support these principles. The first is machine readable norms and policies for the user. So if you remember the little scenario played out earlier, this is allowing every user to describe in a machine readable fashion, these are my terms and conditions if you want to use my data. So there's this W3C standard, ODRL, where if we imagine a user has health data or data about their personal relationships or any other things, then we can have a policy in between them and any organization that wants to use their data. So the ODRL vocabulary states that a policy is described through a set of rules which describe permission when you're allowed to access some target and carry out some actions on those, any duty you may have if I give you permission, and prohibitions where you're not allowed to look. And those rules are described using various operators which act on operands. So here's an example. ODRL vocabularies are described in JSON LD. So I can say here there's an action of displaying a movie, and that that action display is carried out in a movie, and that comes under the permission. So I can give you permission to watch a movie if the current date and time is more than some value, and then that becomes a constraint which fits into the whole policy. Here's an example of a tool built by one of my colleagues in Madrid, and you can see here. You can see there's an API here, and then you can see that there's an operand greater than. If you try to run, you don't get any results because the current temperature isn't above 35, but the current temperature is less than 35, and then you get the result that you can access an IoT device. So the second set of mechanisms is around decentralizing how we manage knowledge graphs. So this packs into a number of separate sub-areas. There's the area of federated query processing. So how can we query distributed knowledge graphs, which are sitting in personal data stores, and making sure for each one that we respect the norms and privacies. Secondly, how can we manage all the tasks associated with knowledge graphs, such as curating the data, integrating the data, validating, distributing, and exploring, making sure that that's transparent and traceable. How can we have explanation methods for the above, including data integration and curation? How can we adjust the management of knowledge graphs for specific runtime conditions and norms and policies, which will be decentralized? So we're adjusting for each individual's user's particular context. What types of architectures and new protocols could support the decentralizing of knowledge graphs? And how do we manage provenance to support traceability? And of course, yeah, solid is a big element of this decentralization. So the third out of 4 is neurosymbolic AI. And this is really not so much a supporting mechanism, but more an extension or an add-on, a complement to knowledge graphs that we need to be aware of. Of course, there's been enormous media attention on generative AI. Through ChatGPT, and of course that's a form of deep learning, which is a form of non-symbolic AI. If we think about the complementary attributes, knowledge graphs tend to be highly explainable and transparent, but they're brittle. They don't really, they tend to work in narrow domains, and if one moves outside of the domain, then they fall over. Non-symbolic reasoning is not so easy to explain, is not transparent, but is not brittle. So in terms of combining these, so the combination of knowledge graphs and non-symbolic reasoning is growing, and the feeling is that knowledge graphs can serve as background knowledge to non-symbolic AI systems. They can aid greatly with explainability, and then they can help, for example, with different types of machine learning by constraining the area. So the final mechanism I'll cover is decentralization. And here there's a whole raft of mechanisms which come under this umbrella. So firstly is online identity. I don't know if people remember this cartoon from 1993 when the web was just emerging. It's a famous cartoon by Peter Steiner, which appeared in the New Yorker, when it talks about the fact that the default was everybody on the internet was anonymous. And of course, that could be an issue. And then in 2015, there was a reflection about this, that actually from then or even before, there is no more anonymity, that everybody really knows maybe too much about you. So from a number of communities, including the distributed ledgers community, there's been this notion of self-sovereign identity. So a digital identity which each user would really own and control. Around this, there are a number of themes or concepts. The first is the idea of a claim, that every user can make a claim. This is my birth date. This is my name. This is my degree that I have. And then for each claim, there can be a proof. And one of the ways of having a proof is attestation. So some government authority saying, for example, that yes, this claim that you're able to drive a car is real. In terms of standards which support this notion, there are two. The first is DIDs, the decentralized identifiers, where basically there's a DID document which refers to a particular subject, which can be contained in a URL, and the DID document also has a controller, which more often than not will be the same entity, which is the subject, and these are recorded on some verifiable data registry, which may be a distributed ledger. Coupled with that is a notion of verifiable credentials. So in the credential space, again, there's a verifiable data registry at the bottom, which may be distributed ledger. And then we envisage three specific roles. So some trusted authority, which issues verifiable credentials, such as a birth certificate or a driving license or a degree, an individual who holds their own verifiable credentials in their own favorite place, and then a verifier. So for example, if one applies for a job, you may have to send your different verifiable credentials, which will have proofs. Underneath this definition is three main elements. There's a credential metadata, which is a background knowledge, a set of claims, and a set of proofs for those claims. So here's an example of that. So Pat is claiming that they're an alumni of a university. And then you can see that Pat is a subject of a credential, which comes from, which was issued by some university and is a type of alumni credential. And the proof of that is the signature from the, which is has the public key of that same university. So again, the underlying description of a verifiable credential is in fact a small knowledge graph. So just to have an example here, this is a particular framework that we created at the Open University, so which we call link chains. So on the left, There are personal data pods in Solid where the underlying data is stored in RDF. There is a distributed data store, which may contain public and private data. And then we have a distributed ledger for the recording, verification, and transfer of assets. And then a particular application or client may access this. So we may instantiate this in an educational setting and say that a virtual learning environment such as Moodle may update the learning record of a student by issuing qualifications for courses token. The metadata is stored in a distributed data storage like IPFS, and then the signing and the proofs are stored on the blockchain. So the data, the actual qualifications are kept in the personal data store, but the signatures and the proofs over encrypted data are stored on the blockchain. So let me talk about a couple of other elements of things that we have created around what I've described. So here's some screen snapshots of a demo for how one might validate Sparkle queries. So this builds on work at the University of Ghent with Communica, their decentralized Sparkle query engine. And then this layer on top was built by my colleagues at the Open University. So we can say that we're querying this source, DBpedia. Here's a Sparkle querying. So looking for resources associated with Belgium. I get a result in here. And then as part of the response, I also get a query plan. So a description of the plan that Communica used to do this. And then I can connect this to a blockchain. So I connect it through a wallet, in this case from MetaMask. And then what happens is I can take the trace data and then anchor all of that onto the blockchain. So take the whole output, including the descriptions and the plans, and then have that as a single blob, which turns into a single hash. Or we can store this per triple. So take each triple in a knowledge graph and then anchor that in the blockchain separately. And then later on, if I want to verify, I can say, okay, here's the, I've just run this again. Is this output I'm getting the same as I anchored? And then you get a verification of results. And if you use the per quad anchoring, you get a per quad verification. So which quads can be found and which quads are not, do not align to what was stored earlier. And then finally, I want to talk about an accreditation use case using this type of framework. So in a project we had running in the UK, we created a national accreditation platform in the area of computer science. So we were working with a number of universities. There were 33 universities in the consortium. And then we did pilots around storing different accreditations. These were extensions to degrees, which would enhance employability, showing that students had a competence in some area. Here's a colleague in the project from the Queen Mary showing one of the badges. We also accredited, as well as an extension to degrees, things like boot camps and summer schools. Here are some students at a OU boot camp where they had physical badges which would link to the blockchain. We mapped elements of a degree to a industrial standard for accreditation. Again, there were 800 different badges for different types of jobs one can have in IT and the different levels of those jobs. And then here's a small movie of somebody who's maybe looking for jobs. So I have a set of my qualifications, and then here you get a list of jobs in the first instance for what I'm qualified for. We're doing information extraction on jobs online and creating a knowledge graph of that, mapping that to seeing where the jobs are, and below is a set of jobs for which the person is nearly qualified for, but there are some skills missing. And then if they like a job, they can see, okay, what online courses could fill in my gaps, and then you get a view of those. So again, without losing any privacy, because you keep all of your qualifications in your own personal data store. And then here we have the job for that. So we also built an app, so each student could see their qualifications, could say, okay, look, I've been offered a job interview at Tesco's in this case, and then I can share my a selection of my qualifications, but for a time limited period. So only for a certain section, only for a certain date, and then after that date, that those qualifications are not to be kept. So again, so I keep control over that. Okay, so just to conclude, there are a number of researchers worldwide, including Tim Berners-Lee, that worries about the over-centralization of knowledge graphs on web data because it allows abuse and silos data. There's all the questions around how can we verify that organization, when they take my personal data, they don't abuse me. We think there are 3 principles which would support decent use of data. That is trust, secondly, accountability, and thirdly, self-determination. And there are 4 main mechanisms, including machine-readable norms and policies for my personal terms and conditions, decentralizing knowledge management, making sure we cover neurosymbolic AI, and then decentralized approaches such as decentralized identity, verifiable credentials, solid and distributed ledgers. That's all I wanted to say. We'll have a follow-on workshop on decentralized knowledge graphs on web data at ESWC. Thank you.
Thanks, John. We have about 5 minutes for questions. Anybody in the audience has a question? Yes, that's one question.
So I can't hear the audience. If,
I'm going to give the mic.
Thank you. I'm Dilip. I'm from DGraph. Thanks, John, for this presentation. Hello?
It's going to be...
Can you hear me now? Hello?
Sorry, try again. Yeah, okay, thank you. Please try again. Okay.
You can hear me, John?
Yes, I can.
Lovely.
Thank you.
Awesome. Maybe this was implied in your mechanisms. I think all those things, they make sense. Do you see like some sort of insurance marketplace developing for these agents? Because I mean, that's kind of where I'm at in my thinking of this. I feel like, we want to, deploy these autonomous, these, KG based supported autonomous agents. And I could see, I mean, maybe it's risky, but I can see some sort of like insurance marketplace developing for this. What do you think about that?
That's interesting. So what that reminds me of, nice question, is what some folks do in smart contracts. So if you're familiar with that concept, so in the smart contract, we agree something, and then if something happens where one of us fails to hold up our end of the bargain, there's a penalty for that. So then one could imagine smart contracts being a sort of insurance agent. You take my data, or there's a community set of data, and then if you do not behave as you should, there's a penalty which we could think of as an insurance for that. So that's the closest term I can think to the question. I don't know if that answers what you were asking, though.
Yeah, I mean, I think it makes sense, and that what you said makes sense in terms of, okay, like what I want the agent to do for me or you, and if there's like counterparties in a transaction. But I'm also thinking in terms of like the legal context, right? Like if the agent like we can have a contract, and the agent is operating in my interest and your interest, but perhaps some external party is being affected, and there has to be some legal parameters around it. And we both, I mean, one of us would have to take that risk. We could say, you know what, why don't we? Some insurance company comes and underwrites the actions of this agent, And so, there's some premium that we'd pay to kind of offload that risk from ourselves.
So yeah, I think it's a great idea. To be honest, we haven't thought about that. Another thing which may again link to the question is I don't know if you've heard of the Data Justice Lab in Cardiff. So they help people who are disadvantaged and maybe people with poor digital skills, and they talk about they call them data advocates. So that's an agent acting on my behalf, for example, for rent or for dealing with online government or online local government. That's not the same notion as you're saying, but there's still the element of another party acting on my behalf and helping me. So I think it's a great point, and I'll bring it to my colleagues.
Yeah. Okay, so that's pretty much all the time we have for questions. I really liked your thing about no one on the internet knows that you're a dog. So there's a saying now, no one on the blockchain knows that you're an AI, and you have this thing, AI self-determination on your slide deck. So I thought that it's kind of fitting because AIs don't really need to do KYC procedures to get a wallet and open up a bank account. All right, so I'm gonna move on to the next presenters. Thank you. All right, so next up, we have Elisa Kendall. She's a lead ontologist at the EDM Council and partner at Thematics Partners, and Pete Rivett, who's here. He's a founding director of Enterprise Knowledge Graph Foundation, and Paul Gazzillo, who's an assistant professor of computer science at University of Central Florida. And they'll be talking about challenges in real-time analysis of ownership and control in banking. I believe, Paul, you're sharing your screen?
Yes, can you hear me?
Yes.
Hello. Are you able to hear me? Hello. Lisa, do you hear me?
I hear you, Paul.
Yeah, we hear you.
Were we not starting at 9:50?
We're starting now.
Okay, all right. Please give me 1 second. Are you able to see my screen?
Yep.
All right. So thank you very much for the introduction. I'm Paul Gazzillo, and I'll be starting the slide. We're going to first talk about this project that I've initiated at the University of Central Florida called the CETA project, and then we'll go into some of our work trying to ontologize some of the data that we're working with in financial tracking. We'll go into more detail about FIBO, and finally we'll talk about Glyph and some future work along these lines. So just to give you an overview about CETA, CETA is the Corporate Entity Tracking Automation Project. And the overall goal, the high-level goal of this is to automate tracking of corporate relationships at a large scale. And the reason for this is not only in the finance world, but with shell corporations, with tax evasion and tax avoidance, with sanctions evasion. There's a lot of interest in government and in private agencies and law enforcement to make sure that we can track how people are moving money around or having influence on industries. We just saw a few weeks ago the Silicon Valley Bank and other bank failures. Government agencies and regulators like the FDIC have a strong interest in being able to prepare and check for stress in these banks, analyze their complexity. There are rules about foreign influence on government contractors, and the subcontracting relationships between these entities can be complicated and make it difficult to actually verify that subcontractors and contractors don't have foreign influence. These changes in ownership and control can change over time. They can change even very quickly. And so even if a year ago, an investigator or a law enforcement agent had validated the lack of foreign influence or validated the structural soundness of a bank, this may change quickly within months or years. And so overall, the approach of this project is to represent relationships as logic and use automated reasoning to be able to query and automatically reason about these big data sets these big data sets that have that record influence across these corporations. So this is the larger project. If you're interested more about the project as a whole, I put the link here to the project website. There's also some demos of the data and some of the analyses that we have on our Appleseed Lab page, which can be seen in the slide here. So the current approach is to represent relationships as a graph, where the entities are nodes and the edges between them are relationships. And then our goal is to formalize the meaning of this data so that we can have a concrete view about what this data means, so that we can actually do queries. Other aspects to this project are taking the multiple data sources that are available for this kind of data and automatically resolving them, aligning them so that we can see, for instance, data from US regulators, data from European regulators, and try to merge this data together. And then also as part of this project is extending reasoning ability, so that we can either take existing tools and extend them or develop entirely new algorithms to try to automatically glean information that's useful to regulators and investigators. But today's focus is on this part, the formalizing the meaning of the data. So the reason for this is that in this particular domain, this corporate entity tracking domain, there's a few problems that are very specific to this. I'm sure there are problems in other domains, but there are some problems that are especially pertinent in this area. So one is that data is fragmented. If you look around just in the finance world, there are lots of different regulators. Each jurisdiction may have their own regulator. Each jurisdiction may define their own scheme for registering businesses. Different jurisdictions have different reporting requirements. So if you go to, say, the Cayman Islands, there's little reporting of beneficial ownership. If you go to the EU, there's much more extensive reporting of this kind of information. And in the US, there's also some recent laws changing this. And they all use different identifiers. So just determining the simple question of, in these two data sets, are the two entities the same? Itself is a hard question, much less actually doing reasoning about what they own. The other problem is that this data is not machine generated in all cases. These are generated by humans. And so there are mistakes, there's partial information, there's inconsistent representation of the same kind of data. So just as an example, if we see 3 data sets and they all have an address field, well, in this domain, address can mean lots of different things. Address could be the physical location of the bank, for instance. It could be its headquarters, it could be a branch, and it also could just be the registered address. So many banks, at least in the US, will be headquartered in, say, New York City, but then they'll be legally registered as a business in Delaware or some other state. And so just knowing what the address of a company is, just knowing what the meaning of that is not a simple problem by itself. So the SADA project is working with several different data sets. One of the most interesting one and one of the most sort of relevant one for regulators is the Federal Reserve's National Information Center. And this is a repository of financial data and institution characteristics collected by the Federal Reserve System. So basically all of the banks and financial institutions that are under the purview of the Federal Reserve. And so this is managed by the Federal Reserve, the Federal Financial Institutions Examination Council, or FFIEC, together with the Federal Reserve and the FDIC, the Federal Deposit Insurance Corporation, who's responsible for insuring banks and taking over banks when there are failures. And so this is a single data set maintained by this council, and it's, I think, collected from reporting requirements that these banks and financial institutions have. And so it's very much for experts and by experts. There's lots of very detailed, specific regulatory and supervision information in this data set. And it's a vast data set. It has banking information going back to the 1800s. It has not only metadata about these entities, but lots of relationships between them, what banks merged, what banks moved their charters. It also has the time series data, so it tells you when these changes in ownership and control happened, how much ownership there is. So just like the address example, if you ask what constitutes control over a bank, the accounting definition is 50% plus one share. But when it comes to banking regulation, this could be as little as 25% would account as control. So this is the NIC data that we're working with, the National Information Center data. And in the CETA project, we've modeled this in our graph database. And there's about 200 or 300,000 total entities that comprises all of the banking and financial institutions that the Federal Reserve knows about and has regulated over time. It's historical, and it has all the metadata about these, lots and lots of metadata. And we just map the relationships between these, the ownership and control relationships, to an edge in our graph database. We also model the regulatory relationships. So there are at least one or multiple regulators that each bank may have, depending on their type of business. And we also map the transformations, that is the mergers, splits, the loss of charter. All of these are in the data, and we've mapped to our graph database. So we use the Neo4j graph database to map all of these. And this allows us, and with our data model and with this database, this gives us the ability to query in pretty simple queries. We can ask, for instance, give me all entities that are directly controlled or in the corporate group of this specific RSSD. So here's an example of what we get when we ask for, I think this is Citigroup. So this query just says, give me all of Citigroup's descendants that it's ever had throughout time. And there's several thousand in this data set. Okay, so we can model this data, and we also have multiple data sets, and we can align them and everything. But when we go to actually do automate some of the regulatory activities on this kind of data, we run into the problem that the data dictionary, the definition of this data, is informally defined. That is, it's in human language, natural language, in a long PDF document. And it's complicated. It's definitely written for experts. It's definitely for those who have institutional knowledge about banking regulation. And so trying to line this up with, say, other regulators in other jurisdictions, or trying to align this data with other data sets is not so simple. So for instance, I mentioned the address, semantics of address, the semantics of what ownership and control is. The NIC data set also has a different definition of what an entity is. So in GLIFE, the legal entity identifier framework, which I think Pete will talk about later, the notion of an entity is, I think, a legally registered business. In the NIC data set, entities can be legally registered business, or they may be divisions of an existing company that, say, if there was a bank merger and a previous bank became a department in a new bank, NIC still treats these as entities. So one of our main goals of this project, and something that Elisa and Peter will talk about after this, is the goal is to formalize this data. And if you look through this, it's several pages of very complex, detailed technical jargon that I'm sure banking regulators are very familiar with. But it's definitely designed for experts in this. And the definitions for these terms are not just in one location that says, here's what, for instance, a non-bank is. These are spread across statutes and policies, the International Banking Act, the Bank Holding Company Act, and these change over time. And so trying to understand this requires understanding what the data looks like, but also all the legal definitions, which are completely a social construct. They can just change due to an act of legislation instantly, or at least at one point in time. So part of the problem is trying to track down all of these supervision and policy documents, statutes to describe what this formal data means. Another reason that we want to formalize this is that it'll help us align other data sets. So things like address and jurisdiction, we can use more intuitive notions or look at the data sets as a non-expert and understand how to align these. But trying to do this with the more intricate banking regulation information is more difficult. And so as Elisa will talk about next, our goal is to have a formal semantics of this, expanding FIBO, the financial industry business objects. And the benefit of this is that it's a centralized schema as a target that we can map all of these data sets into, so that when we do our modeling and we do our analysis, we'll have a single semantics that we can use to understand this. So with that, I'll hand it over to Elisa.
Okay, so one of the things that Paul mentioned and that we really want to highlight here, and that's relevant for this particular workshop, is that the real world, especially in the last couple of months, changes a lot faster than the data in the various data sets that we're working with. So the data in the real world related to Silicon Valley Bank changed overnight. The data this week for First Republic changed overnight. And regulators need to be able to see the current state of the world at any point in time, and also predict where they think that world is moving, depending on the situation. And it's not just limited to regulators. Anyone in a particular industry who's doing any kind of market research needs the same things, right? They need to know if you're, say, a pharma company and you're thinking about partnering with another organization, which they do all the time, you need to understand the relationships that those businesses have to others to understand if you're actually partnering with a competitor or not. So there's a lot of value in the same patterns and in understanding the semantics of them, regardless of whether you're doing a regulatory job or whether it's a corporate application. And so moving to integrated technology, allowing us to really improve on the connections between the data and allow people to do these kinds of analyses is really hard. And that's partly because of the descriptions and definitions available for these data sets. And pulling together multiple data sets that are structured or unstructured data, other sentiment related content, all of that's really, really necessary to get the big picture. So the NIC, which is the repository that Paul just described, only contains details about banks and other related legal entities that are regulated by, say, the Federal Reserve or the FDIC or some other U.S. regulatory body in the finance domain. But there are other details that show up in other data sets that are really useful. Hard to integrate with the Federal Reserve data, but really interesting. And people share something about the Global LEI Foundation's GLIFE data. Other data sets that some people are familiar with include open corporates, and there are a bunch of proprietary data sets that track information about these organizations. One of them used to be called SNL, is now part of Standard & Poor's, and they have a much richer ownership and control hierarchy, and details of the percent of ownership and things like that derived from SEC filings, from other bank filings, from various stock trades and things like that they keep track of for bank stocks so that they know who has a high percentage of ownership at any point in time. Bloomberg, Thomson Reuters, and other data providers in the finance space do the same. And of course, they all have different data dictionaries. A lot of the data is not necessarily easily aligned. The definition of what is a branch, as Paul mentioned, versus what is a full up agency, whether it's an agency of a US bank or an agency of a foreign bank. All of that kind of stuff is outlined in the NIC data, not necessarily available in these other data sets. On the other hand, the NIC is missing a lot of the intervening ownership and control data for legal entities in the middle that they don't regulate. So the challenge is pulling all of it together so that you get a bigger picture of what's happening. And even with that, you're still not going to know that a bunch of VCs told all of their companies on their private Discord channels to pull all their money out of the bank. I mean, which is exactly what happened overnight with Silicon Valley Bank, right? So the challenge is we can try to gather as much as possible, try to pull together certain sources that are of interest to either the government or some other business entity that is investigating their partners. You can pull together some of the sentiment. You can pull together a lot of unstructured data. You can pull together structured data sets. You may still not really know what's going on. Okay, next slide. So in order to at least have a prayer of mapping some of this stuff, we're looking at FIBO, which is an industry-level ontology, as the basis for at least some of the standard terminology, the relationships, and the logic that help you reconcile some of these disparate data sources and map them to one another. That does not mean that we would tell you that you need to manage all of your data in a single knowledge graph. And in fact, the opposite is true. You only want to keep the content that is relatively stable in a knowledge graph that's FIBO based. And then you want to query external data sets with mappings that you create wherever they live. And so, in this sense, we're talking about centralized semantics, but decentralized knowledge to enable you to stay current. So FIBO, just to provide a little bit of background for folks that aren't familiar with it, it started out as a project that some folks worked on at the EDM Council in response to the financial meltdown of 2008-2009. And there was a ton of regulation in the US and in Europe around that. And some of that legislation mandated the use of controlled vocabularies and definitions that everybody agreed to, so that at least within an institution, they were using the same terminology consistently. And that content was transformed actually by Pete, who's presenting next, to OWL in 2013. We've added an increasing amount of process around it, governance around it, and need to do even more in that vein going forward. It was first released as a joint standard between the Object Management Group, where Pete and I are both very active. He's been on the architecture board with me for many years, and the EDM Council, where I'm now lead ontologist, starting in 2015. And we have quarterly releases that are reviewed by domain experts, guided by now multiple ontologists. Those are published on the EDM Council site. The link is here in the slide and available on GitHub. And so you can download it, you can look at it, you can send us issues. It's open source and anybody is welcome to use it. But what it doesn't include is some of the data sets that we're talking about here. So the goal is to actually use FIBO and extend it to facilitate some of that mapping and standardization of language. And just by way of one anecdote, there was a project that I worked on with a bank in the Nordics in, I want to say 2017, 2018 time period. And just within that bank, through acquisitions and mergers, through integration of a gazillion different software systems at those various banks, they had 11 definitions for one term, which is one of the most basic terms in finance, which was nominal amount. 11 different definitions for an accounting term. And we were able to help them using FIBO and other internal resources get it down to 2 definitions but we weren't able to get it down to 1, which is sort of the holy grail here. So at any rate, FIBO can help with that, which is what we're working with Paul to do. So next slide. So there have been a bunch of different use cases that have driven FIBO over time. Here are a few of them. One of them was that the Dodd-Frank in the US and MiFID II framework in the EU, developed by the European Commission, required financial institutions to use a standard business glossary. And FIBO is in use now by a number of different banks for that purpose. So we were also asked to cover some of the data governance, data management, and other glossary requirements that the Basel Committee on Banking raised for risk data aggregation. People are also using FIBO for that. We're also trying to address some of the emerging regulations in the EU and the US for things like data privacy, and for more transparency in the data, dealing with things like hedge fund short selling of a couple of years ago, the insolvency of Silicon Valley Bank, Signature Bank, and when I wrote this slide, First Republic had not yet been purchased, but I believe that's happened as of this week. So FIBO can help with those things, giving you a common basis for understanding the complex financial instruments involved, the relationships between counterparties, ownership and control relations, and other risk mitigation support. And we're also working towards addressing some of the requirements for things like the Financial Data Transparency Act, which became law in the US in December, for consistency in definitions and formats across the various financial regulators in the US to help them work together better to address some of these problems. Okay, next slide. So here's FIBO at a glance as of a couple weeks ago. On the left-hand side, you can see in this image from Protege some of the statistics. We actually provide quite a bit of reference data, which is why the individual count is so high. But it's a big ontology. It's got a lot of classes in it, lots and lots of properties. And so it's not small, and it's increasingly consistent, which is a good thing. And so just to give you an idea for mapping to the data that Paul's been talking about, a partial list of our financial service providers, definitions for different kinds of banking entities like holding companies or clearing houses or central banks or other kinds of depository institutions and so on. We have a fairly rich hierarchy, which we've been extending to include the legal definitions for some of the entities defined in the NIC. Okay, next slide. So here again is the slide Paul showed with respect to the data dictionary for the NIC. And just to give you an idea of how hard this is, there's a whole list in that center of the entity types that are defined in the NIC with very little in terms of detail telling you how they're different from one another. And to date, we've been able to find in the regulations definitions for most of them, but there are still a few that are challenging. So there's a thing called a twig, which is a branch of a foreign bank that is managed by a branch or an agency of a U.S. bank and owned and controlled by a foreign bank. And so we've got most of that down, and we have all the restrictions that say, you know, who owns who, under what circumstances. But then they add a twist that says, okay, if it has this certain kind of regulatory reporting requirement, then it's this animal. And if it doesn't have that, it's this other thing. And so that I haven't found yet. That's hiding somewhere in the regulations and in likely letters from the regulators to the various entities they control. And there's some arcane difference between the two in the law that we might have to go to banking attorneys to sort out. Okay, next slide. So here's an example of what we've done in order to represent certain kinds of financial institutions. And you can see in the top, we've added the links to the legislation, and the definitions come right out of the legal documents. And we can do this for any jurisdiction. It doesn't have to be the U.S. FIBO allows you to segregate by jurisdiction. So we've done that here. And then at the bottom, the code from the data dictionary is aligned with the definition of the entity and all of the restrictions we have to describe it in FIBO so that we can do the mapping automatically. And that's just one example. Okay, next slide. So some next steps for us, we're going to keep building out those definitions and digging into the regulations to figure out what the heck they mean. And likely at the end of the day, we'll need assistance from banking attorneys to do that, as I mentioned. We're working with Paul to help map more and more of the data to FIBO so they can convert the current graph to something that is more knowledge graph based. We're going to start to build out some formal set of competency questions with sample answers so we can do some analysis and regression testing and prove that the mapping works. We're identifying more and more extensions we need to make to FIBO in the process, and other content that we should be integrating, limited only by our imaginations at this point, but to include things that the regulators care about, like the Global LEI Foundation data, and integrate that with the core graph. Okay, Pete, over to you.
Yeah. Okay, thanks, Elisa. So what I'm going to move on to is some of these different data sources in addition to the NIC. So NIC is providing the core data source that Paul talked about. FIBO is providing our target in terms of the semantics, but there's other data sources out there that we've talked about. And in particular, I'm going to focus on the Glyph data set. This is just an example of the same information from NIC and from Glyph, and I'll show you more information about that specific bank in the next few slides. Next slide, please. So Glyph is the Global Legal Entity Identifier Foundation. So the notion of the LEI came up after the 2008 crisis. This was a worldwide initiative. And the big problem they're trying to solve is that no one really knew who their exposure was to. Because all these banks, these financial institutions had sort of variations on the same name. They didn't really know, is this the same entity called X Bank, or is this entity called X Corp Bank the same entity at all? So they wanted a unique identifier worldwide and mandated by various regulations. So for certain financial transactions now, and this is, as I say, worldwide, you need to have a legal entity identifier to participate in that transaction, so everyone knows exactly who that institution is you're dealing with. So there's a single, opaque, and verifiable identifier. I'll say a bit more about that in a moment. And it's registered by local operating units. So there's a large number of local operating units that do the registration. It includes like London Stock Exchange is one, Bloomberg is another. They can be transnational, they can be national. So the idea is, in order to participate in these contracts, then you need to register for a legal entity identifier. There's a small charge, which I think is about $50 annually, and you do need to review it. You do need to attest every year that the information is still valid. And then all this is brought together by the Global Legal Entity Identifier Foundation, which runs the whole process. It takes feeds from all of these local operating units and creates a consolidated data set. And you can go to glyph.org and look at that, and I'll say more about that. So currently there's about 2.1 million entities registered worldwide. And by the way, it's not restricted to financial institutions. My own little consulting company has got a legal entity identifier as well, just so I could prove the process and understand as a participant how that works. So pretty much anyone can register for an LEI. Another interesting thing tying in with the first presentation we had today is that what Glyph has recently introduced is a thing called the VLEI, the verifiable LEI. So that's very much picking on the idea we were talking about earlier in terms of verifiable identity. That allows people to, or organizations to verify that given individuals have a verified role for that organization. So this person is verified to approve various financial transactions on behalf of the organization. Not sure what that noise is. Okay. This person is the CEO. This person is employed by the organization. So this is a new addition to the LEI, the VLEI. It's still quite new, but it nicely ties together the first talk today with the notion of a legal entity identifier. So you actually know the person who's purports to create an invoice or ask for money is actually the person who's entitled to ask for money from your verified supplier. There's the other important thing, two other important things that the LEI data set includes. One is a link to the original registration for the business or the company. Like if a bank is registered in Delaware, the LEI includes the fact that it was registered in Delaware, who is the registration authority for Delaware, and what is their unique registration number within that authority. So you can trace back to how the business was originally registered, and that allows people to verify whether the business still exists in its original jurisdiction. And very important in terms of financial exposure, you've got parent company controlling information, which is called level 2. So level 1 is just who is the legal entity, what's its address, and it includes the distinction between the registered address, which might be in Delaware, and the headquarters address, which might be in New York. This is all verified. But it's also got the controlling information, and the specific semantic definition in the Glyph data set is called a reporting consolidation. So that means if company A includes company B as part of its consolidated financial report, then that's included in that data set as a level 2 information. And that includes both immediate control owning company and ultimate owning company. So even if there's some gaps in the middle, as Elisa and Paul were saying earlier, you will get the ultimate controlling company as well. The data set as a whole is updated daily, in fact 3 times a day more accurately, and you can obtain it from the Glyph site as a set of daily diffs or as a complete set. Next slide, please. So that data set was around for a while, and it is published primarily as XML, and they also do publish it as JSON and CSV, but that's a bit harder to deal with. What I did in conjunction with Data.World and co-funded by the Glyph organization and Data.World was create an ontology representation of that, very much inspired by FIBO, but slightly simpler than FIBO, because we didn't have the notion of financial instruments and so on. We just wanted to represent the legal entities and their relationships and addresses and so on. So there's a complete ontology represented in OWL, and it's available as RDF and HTML. You can follow all those links to the ontology. It's registered in the linked open vocabularies encyclopedia, which is a good resource for finding all sorts of ontologies. And then the ontologies themselves and the data, very importantly, the data is available on Data.World. So effectively, every day there's a bulk job that applies XSLT and Python to take the complete data, which ends up being like 100 million triples, the complete data set. So that's published every day on Data.World, and you can query it. It's all the source code for that transformation is also available as an open source project on GitHub. So if you don't want to download it from Data.World, you can actually download the code and run it yourself against the original Glyph source. Next slide, please. This is just an example of the Glyph data set showing Silicon Valley Bank. So this is the original Glyph site. You can go to glyph.org, query by using the LEI or by using any name. And this is Silicon Valley Bank. It shows you their basic information, the address information, all the other things which might be called Silicon Valley Bank, but the LEI identifies which one you're dealing with. Next slide, please. And this is the where it was originally registered. And next slide, please. Then more recently, we extended things to cover the events. So you can see one of the events for Silicon Valley Bank was its dissolution. So it does somewhat depend on regulators or whoever to report information to GLIFE, because legally it's only required to be updated annually with the renewal. Next slide, please. So this is, I'm not sure how we're doing for time. This is a link to the data.world site. And what we've got as a project on data.world, which you can see there, is not only the raw data set, but also a bunch of sample queries. And this is a sample query you can run if you click on a link, and it will show you a pre-filled query with that data set and all the information about Silicon Valley Bank. So I'll leave that for people to look at, given we're a bit pressed for time. Next slide, please. So in summary, what we've been doing then is taking a bunch of these different sources. GLIFE I've just talked about, which we've mapped to FIBO. The NIC for Federal Reserve information, Elisa talked about being mapped to FIBO, and other potential business registries and sources of information. For example, Open Corporates is one, OC. And in fact, just today I saw an announcement from GLIFE and Open Corporates that they're going to be partnering a lot more closely. So Open Corporates will now include the legal entity identifier information in the information they've harvested and published on their site. So that brings everything neatly together. And what we've shown by this mapping is common semantics across the two. So even though all the data isn't in one place, you've got the common semantics, you've got the ability to build these federated queries that pull everything together. Next slide, please. So where do we go from here? What are other options? We talked about a number of specific data sets. Where can we go from here? And in particular, how can we address the need for real-time responsiveness to things that are happening in the financial industry? So one thing we can make use of is that these banks and companies in general are required to make SEC filings to the US regulator regarding shares and ownership. So there's a number of specific ones, for example, 13D. If someone gets a holding of more than 5% of a company, that needs to be reported to the SEC within 10 days. So that's the thing that Elon Musk was somewhat tardy on when he took that big shareholding in Twitter. So 13G is similar but more relaxed. This is for investment houses and banks investing in other companies, where they do tend to have a lot of, they may have more than 5%, but it's more as part of regular business. So they've got more relaxed timing on that posting. Then there's quarterly investment management reports, where an investment fund, like various Fidelity funds, for example, and Vanguard, they need to respond they need to respond quarterly for any holdings above 100 million. And there's just annual reports for everyone, and also annual reports for large traders who are trading more than $20 million a day. And then one important thing also is the 8K reports, where certain events such as management changes need to be reported within 4 days. So all these are public, they're queryable, they're in machine readable format, some of them, in others more easily parsable text formats. So those are options for bringing in more real-time information into the integrated knowledge, integrated semantics, but distributed storage. And then the other thing is social media analysis. There's a good report I linked to here where they analyze and they showed that by looking at Twitter posts, for example, in particular from certain types of account, they would have been able to predict some of these disruptions in financial market. Those are things we can look at in the future. And then final slide. So questions for consideration as part of this overall architecture. So what is the balance between what we should ask for in terms of regular pushes of summary data, in particular from banks, as opposed to on-demand regulators drilling down and asking banks for more information if they see some sort of flag is hit and there are warning signs? And should the latter be a dynamic query that a regulator does to some sort of open interface that the banks make available, or should it just be the banks saying, okay, give us this more detailed feed, and that gets pushed back? And what are the technical and financial implications on banks being able to put this sort of infrastructure in place, and on regulators being able to make the outward requests to process these queries, and which copes better with change in terms of the detail? And and we already talked about decentralized semantics and handling changing semantics. Right, summary then, next slide. So we're seeing new threats to financial stability almost every month. The existing NIT repository is hard to understand and extend and supplement with existing data, but the knowledge graph approach promises the common core semantics based on FIBO, the integration capability via the identifier mapping, and the extensibility, while providing the flexibility for unforeseen events, because you can easily extend an ontology to either extend the existing ontology or have extended queries that bring in new triples.
All right. Thank you, Pete, Elisa, and Paul. Since we are very short on time, maybe we have a very quick question, and I encourage others to catch Pete during the break.
I'll be around the rest of the week.
Hey, nice presentation. So my question is kind of tangential to this thing. So we have I work for investment firms. We have market data, reference data that comes up in the XML formats. One of the problems that we have is we don't get change data capture. So every day we get a new snapshot. And the problem with that is we can't actually build a graph or some kind of queryable. So every time what we do is we depending on the client's requirements, we go through the paths, pull them up, and store them in a structured database. So I was just trying to gauge your understanding or thoughts on it, in terms of the change data capture for this kind of market data or reference data and the problems that we face.
As I mentioned earlier, Glyph specifically does provide daily updates as a set of diffs, but they're more if information about an entity changes, they don't just provide a set of diffs for that entity, they provide a complete entity, new version of that entity. But there are techniques available, in particular, if you're looking at RDF and quad representations, you can actually, and there's actually a standard I can refer you to, or de facto as opposed to W3C standard for representing change sets in RDF, and I've done quite a bit with that. And there's some open source technologies out there that allow you to compare two RDF data sets and create the diffs, and then you can do versioning based on the change sets too. And you can track versions over time, you can see change history. So there's a fair bit developing around that notion.
All right, so I think we have to finish your talk, and I encourage people to catch Pete during the break. So next up, we switch gears from traditional banking to more Bitcoin-oriented network analysis. So we have Kaiwen Zhang. He's a professor with the Department of Software and IT Engineering from ETS Montreal. And he'll be talking about using graph theory to analyze the Bitcoin network. So this is a short presentation. It's a 10-minute presentation, and then we'll have the break after that. Over to you, Kaiwen.
All right. Thank you, Oshani, for the introduction. So good morning, everyone. So today I'll be presenting some of the work that I've done with my student, Yahya Shasavari, and my colleague at Montreal, Shamsuddin Tali. So let me first give you a little bit of context on this. So I think a lot of talks we've heard so far, and some of you are going to be hearing in the afternoon, are going to be about how to leverage blockchain technology or smart contracts. We also heard DIDs for maintaining or using knowledge graphs. So in my talk, I wanted to go the opposite direction. So I wanted to explore something different, which is how can we use knowledge graph, or more generally graph theory in general, to analyze or study blockchain technology or existing blockchain applications like cryptocurrencies, which is the topic today. So when we first started, we didn't think necessarily about using graphs, but we were thinking about what's called performance modeling. So that is using mathematical models or simulation to estimate or predict the performance of a blockchain system under certain configuration. So the reason why we do that is because, well, from the original Bitcoin code, it has spawned many thousands of different cryptocurrencies, which we call altcoins. And often these altcoins tweak the core code of Bitcoin a little bit. So maybe they'll increase the size of the block, or they'll make the block time shorter, but it's not understood what is the impact of this on either the performance of the system or the security of the system. And so that's where we come in with our mathematical models. So where are the graphs then involved in this performance modeling? So just a quick overview of what is a blockchain network. So of course, the data structure on the left side, I won't be talking about that today. It's not relevant for the talk. I'm going to be focusing on the right side of a blockchain network, which is this what we call the peer-to-peer overlay network. So it's an unstructured network where all the miners, or we call them also full nodes, connect to each other in any way they want. They can choose their neighbors. This is a decentralized network to form this network that's going to be maintaining this blockchain data structure. And so this overlay network can then be modeled as a graph, and that's how we're going to do our performance modeling. So over the years, we've done several contributions in this domain of performance modeling for Bitcoin and blockchain networks in general. So I list some of them. So the basic or the first work we did was to introduce a concept of waves, and using what's called random graph, so more specifically Erdos-Renyi random graphs, to model what's called the block propagation. So how those blocks propagate in a Bitcoin network. So we published that first. Then we also studied how the Bitcoin network can fork. Okay, so sometimes the consensus is not perfect, and the blockchain starts to diverge, and then it comes back together, it merges again. So that's what we call a fork. So we try to calculate what is the probability that a fork happened, because this is a threat to the security or the health of the network. We've also considered extensions to the Bitcoin protocol, like the compact block protocol, and also another concept called the relay network for Bitcoin, which is supposed to enhance the performance of the blockchain. So we've studied how much does it enhance the blockchain, but also it has a trade-off, and it affects the decentralization of the network. So we've also quantified this impact on decentralization. Today, I'll be mostly focusing on this and just giving you a brief outline of the first work that we did here. So in this first work, our starting point was to say, okay, what is an idealized Bitcoin network? What is an idealized decentralized network for a blockchain? And what the model we found is what we call a Erdos-Renyi random graph. So meaning that all of the different participants of your network, so the vertices would have a certain probability to be connected to anybody else, and it's a uniform probability. So that's why we call it idealized decentralized network. But in reality, well, yeah, you have preferences. There are influences that might make some peers more popular than others. So we actually model that in another work using what's called the Barabasi-Albert model using preferential attachment. But in this one, we just talk about the ideal network. And so each node has a probability P to be linked to another one. And as you increase the value of P, you make a more densely connected network. So the first thing we just wanted to understand is what is a good value of P for two reasons. First reason is for security. So what would be the minimum bound for P so that your network is safe, your Bitcoin network is safe? So why would that be a problem? So if P is too low, that would mean that you start to have disconnected components in your graph. Okay, so that's in our distributed system, we call that a network partition, and that's very bad for blockchain because you're supposed to synchronize all the information at all time together. So if you cannot reach a component in the graph, then you won't be able to complete this synchronization. So according to graph theory, P has to be greater or equal log n of n. N is the total number of machines in the network. And for us, we converted that into a more useful indicator, which is M as the average connections per node. And so the minimum safety threshold is M is greater or equal the ceiling n minus 1 over n of log n. And so once we derived this information, we wanted to test whether the Bitcoin network is actually safe. And so online, you can find information about the size of the network. So at the time we did that, it was around 10,000 nodes in the Bitcoin network. Nowadays, it's more like 17,000 nodes. And so according to our calculation, M had to be equal 4 at least for the network to be fully connected so that it is safe. And luckily, we found that the Bitcoin default parameter is 8 connections per node, so it is way beyond the threshold. And actually, the reported average is 32. So the next question was to think, well, what do you gain for maintaining more connections over the 4? And what you gain is performance. So yeah, in the work, what we do is we continue the modeling to calculate what is the optimal value. And the spoiler here is the answer is also 32. So we were able to validate that the current parameter used in Bitcoin is actually the optimal value for performance, at least. Okay, so that's all I wanted to say today. So what I presented was the use of Erdos-Renyi random graph for modeling Bitcoin networks, and that's how we we calculated the lower bound on the number of connections. In the paper, we also calculate other metrics like delay, traffic overhead. We've also implemented it in a network simulator called OmNet++. Our empirical findings are validated. So 32 is the optimal value here. In other works, we also calculate the fork probability, and if there's a fork happening, what is the weight of different branches for a competing block. We've also calculated what is the impact of a relay network and the impact on decentralization, but that took another graph model, which is the Barabazi-Albert graph model, to do that. Okay, so if you're more interested, please go ahead and read our papers. You can also visit the website of my laboratory, where we do lots of different technical research on blockchain systems and applications. Thank you very much.
All right. Thanks, Kaiwen. Any questions from the audience for Kaiwen? If not, I have a quick question for you. So you did this for Bitcoin. Do you imagine a similar thing to play out in other blockchains like Ethereum, or maybe even more interoperable chains like Cosmos or Polkadot?
Yeah, this is ongoing work to study maybe layer 2 systems like Polygon. We've already studied Ethereum, at least the proof of work version of Ethereum. Now it's since it's updated, I think we got to do it again. We've also studied blockchain systems, such even the ones by Facebook, Meta, which is called Libra.
Libra, yeah.
Or DM. Okay, so we studied that one, but unfortunately that system didn't go. So we did that. We've also studied other kinds of variants of Ethereum, like Quorum, that maybe are useful in CBDC, for example. And Hyperledger Fabric as well is another one we studied.
All right. Okay, so I guess everybody needs the coffee break right now. So we break for I guess roughly 24 minutes, and then please come back because Origin Trail will be talking at 11 o'clock, and we'll have some other talks as well. So see you back here at 11 o'clock. Thank you.
Thank you.